Hello, I'm Mr. Bob, and welcome to my Algebra 1 video series. This video covers Chapter 4, Section 2, titled Proportions and Similar Figures. By the end of this video, you will have reviewed proportions and similar figures. You will work to understand the concept of similar figures, and then be using that understanding to find the lengths of sides of triangles. From there, you will review methods for making indirect measurements by applying the concepts of similar figures. Then you will end this review by looking at computing distances on a map and using some dimensional analysis that you reviewed in a previous section of this chapter. If you would like me to cover any of these topics in greater detail, please leave a request in the comment section below. Please subscribe to this channel if you find this video to be helpful. Thank you, I'd appreciate it. Okay, a couple definitions before we get started. You'll see these again in this section, but I'll go over them. I like to just put them in your mind so you're thinking about them before we actually get to it. Scale drawing. A scale drawing is an enlarged or reduced drawing that is similar to the actual object or place. A scale, because we said scale drawing, but in this case, a scale is the ratio of a distance in the drawing to the corresponding actual distance. And that is a scale of the drawing. That is the scale of the drawing. You hear it in terms of like feet per inch or whatever, miles per inch, that type of a thing. It's the scale. Okay, objective one, similar figures. In the diagram below, triangle ABC and triangle FGH are similar. Similar figures have the same shape, but not necessarily the same size. And the symbol right here, this symbol right here, we call it a tilde on your keyboard, means is, if you see this, means is similar to. Okay, so having to do with similar triangles, similar square, whatever, similar figures is similar to. That's the little tilde right there. In similar triangles, corresponding angles are congruent. Here's like an A and F. Those are corresponding angles, okay? Because they're in relative to the shape and position, everything here of the shapes of the triangles, those are corresponding. The sides are proportional. The order of the letters indicates the corresponding angles. If ABC is similar to FGH, then the following is true. So let's look at these. I'm going to change color to a darker color now. Angle A, right here, angle A, that's what I drew the circle on earlier. Angle A is congruent. This symbol here means congruent. The equal sign with the tilde above it, right there, congruent to angle F. And I said that, I pointed that out earlier, that these are congruent. They're in similar triangles. These are corresponding. And then angle B right here is congruent to G, and angle C is congruent to H. And then when there's C and H, okay? In terms of the lengths, we said that they were proportional. So AB is proportional to FG. So A, right here, AB, it's 8, right? Is proportional to FG. AC is AC is proportional to FH. AC, right here, AC is proportional to FH. And then find the last one, BC, BC is proportional to GH. Okay, and then look at the numbers, 8 and 12. Here's 8 and 12, 10 and 15, 12 and 18. These are all equal to each other. So 8 divided by 12 is the relationship. 8 divided by 12, 8 divided by 12 is equal to 10 divided by 15. And 8 divided by 12 is what? It's 2/3. 8 divided by 12 is 2/3. 10 divided by 15 is 2/3. And 12 divided by 18 is 2/3. Each of these is equal to 2/3. Okay? Okay, example 1, finding the length of a side. In the figure below, it's over here actually to the right, triangle ABC is similar to DEF. Find DE. So they want us to find, where's DE? DE, right here is X. They want us to find X. And we're going to use the proportionality, right? So what are we going to say? We're going to say relate AB is to DF. AB, this is this one here, AB is to DF, and you can see there's this similar sides as AC. AC is to DE. And DE is the X that we're looking for right here. Here's our X, right? I'll change colors. It's our X right there. So given that, we're going to take now and we're going to let X be the DE length. That's what they tell us to do. And when we've done that, we're going to write 15 is to 10. So 15 is to 10, the size. 15 right here is to 10, the relationship. This big side here, I'm going to change this color to a darker blue. This line right here, and these are going to be related. 15 is to 10, right here. 15 is to 10, as 21 is to X. Well, here's 21, and this is proportional to the DE side, right? Here's our X. So we wrote it, 21 is to X. Now there's our relationship. 15 over 10 is equal to 21 over X. Now we're going to solve the equation. We're going to solve for X. So we're going to cross multiply using cross product multiplication. We're going to multiply the 15 on the left-hand side by X. Here's 15X. And we're going to multiply the 21 on the right-hand side by 10. Okay, and here's the 10 times 21. So we have X. So now if we simplify this and carry out the next operation, we're going to divide 15 to both sides of the equation. So we're going to have, it was 15x is equal to 110. Now it's x, because we're going to divide by 15 right here. X is equal to 210 divided by 15. So x is equal to 14. So DE is 14. So again, all we did is we said that we had the relationship 15 is to 10 as 21 is to X. That's the relationships. And I'll show you something else. You could have written it 10 is to 15 as X is to 21. Same difference. But you wouldn't have had to move the X anymore. You could have just said 21 times 10. Sorry for that. Let me undo that. It's a little messy. Let me do that. You could have said 21 times 10. That's moving the 21 right here up to here, divided by 15. And that equals X. You just done the 210 divided by 15, you would end up saying X is equal to 14 with a fewer step. This one took extra steps up here. Okay? Hope you get that. Okay, example 1, check your understanding. So if you've worked with me before on these, you know I want you to stop the video and try this out. And then when you come back, we'll work them together, okay? So I'm waiting for you. Okay, now that you've had time to work this out, let's go ahead and see if we can work it together. So we have two triangles, and they're giving us a couple measurements, and they want us to find, what they're looking for us to find is this section right here, which is this LM. It says find LM right there, find LM. And they gave us 3 other dimensions, and we need 3 to pull this off, right? So, and I'm going to do it like I showed you at the end of the last slide. I'm going to call this x. LM I'm going to call x. So I'm going to say here that x, let me change the color. Let me change that color to something a little better. Here, so first let me erase that and change it to a brighter color. So I'm going to say x is to, well, the corresponding lines here are GH and LM, they're corresponding, is to 20 as, as we said before, equals is always as, okay? And then we could say as 24, we have to start with the same triangle. So we're going to 24, the corresponding side is to 32. Okay? The rest is all simple. We're going to take and we're going to multiply both sides by 20. So we're going to, x is equal to 24 times 20 divided by 32. That's the cross product, kind of cross product. We didn't do cross product, but we canceled the 20 on the left-hand side. So now we have x equal to what? X is equal to 480. Oops, 80. 24 times 20 is 480, and that's divided by 32. And if you divide 480 by 32, you're going to get 15, and it is centimeters. 15 centimeters. Okay? Objective 2, indirect measurement and scale drawings. So we're starting to move in that direction now. You can use proportions to find the dimensions of an object that are difficult to measure indirectly. Like if you wanted to find the height of a building, we're going to show you here that you could use, for instance, your height and and your shadow and the shadow length of the building. And those are three dimensions you can get. And from that, you can, like we just did in the previous slide, you can get the height of the building. They're going to show you that with trees here as we move forward. Okay, example 2, applying similarity. A tree casts a shadow that's 7.5 feet long. Right here, 7.5 feet long shadow. And that they're showing you it right here, 7.5 feet, the tree's shadow. A woman, 5 feet tall, here she is, 5 feet tall, okay, casts the shadow 3 feet long. So her shadow is 3 feet. So here's the tree shadow, and we're going to try to find out how tall the tree is right here. And we have similar triangles because the sun causes the correct same ray on both of the tree and the lady. Okay. The shadow is proportional to the angle of the sun. Okay. So the triangle shown for the tree and its shadow are similar to the triangle shown for the woman and her shadow. How tall is the tree? Well, we're going to start off by saying 3 is to 3, her shadow length is to the tree's shadow length as 5, her height, which we know is 5. I'm going to write that in here. 5 is to x, and x is the tree. This time they put the x on the bottom. I would have probably flipped it like we did in the previous slide, but not a problem. So now that we have that, we're going to cross multiply. We're going to write our cross product multiplication. In doing that, we're going to take the x up to the 3 on the left and have 3x. And we're going to take 7.5 from the denominator on the left and multiply it to the numerator on the right. And we're going to get 7.75 times 5. And then we simplify it. We're going to get 3x is equal to 37.5. And that's going to give us x equaling 12.5 feet because we're dividing both sides by 3. Divide by 3. The tree is 12.5 feet tall. Okay, example 2, check your understanding. So as you know, I'd like you to pause the video and try these first. And when you come back, we'll work them together. But I'll read them to you before you leave. A tree casts a 26-foot shadow. A boy standing nearby casts a 12-foot shadow. His height is 4.5 feet. How tall is the tree? And problem B says a house casts a 56-foot shadow. A girl standing nearby casts a 7.2-foot shadow. Her height is 5.4 feet. What is the height of the house? Well, why don't you go ahead and try it, and when you come back, we'll work these together. Okay, now that you're back, let's go ahead and give it a whirl. So we're going to look at first problem A, and we're going to have a tree casting a shadow. So I'm going to draw a tree, a little tree. That's the top of the tree, okay? Here's the bottom of the tree, right? Some leaves all over the tree, all around. So the tree is casting a shadow that is 26 feet. 26 feet. Okay? And we don't know how tall the tree is. That's what we're probably going to how tall is the tree? That's X. We're going to let the height of the tree be X. And then it says that a boy standing near the tree, I'll put the boy down here, standing near the tree, the boy standing near the tree, and he has a shadow. His shadow is 12 feet long. 12 feet. And the boy is 4.5 feet tall. So what are our we have X. These are the relationships. X to 26 is 4.5 is to 12. So let's write it. X is to 26 as 4.5. The boy's height is to his shadow, 12. So the tree's height is to its shadow as the boy's height is to his shadow. Now we're going to multiply both sides by 26. Okay? And that way we're going to cancel. I'm going to say X times 26 divided by 26 is equal to 4.5 times 26 divided by 12. Okay? Now we're going to simplify. So we're going to get, these are going to cancel. We're going to get X is equal to 4.5 times 26. So 4.5 times 26 divided by 12. And that equals, if you do the math on it, 9.75 feet. That's the tree's height. Okay, let's do the house. A house, here's our house. Well, I'll try and draw a little house here. Okay, we got the height here. Here's our house. And it casts a shadow out here somehow, however I can draw it. It's going to cast a shadow that is from here, like, what does it say? 56 feet. 56 feet. And we're going to try to find how the height of the house. The height is X. The height of the house. Okay? Now, and it says a girl that's 5'4", so I have a little lady here. Okay, I'll put a dress on her. Now she is 5 feet 4 inches tall. Oh, not that 5'4", 5.4 feet. 5.4 feet tall. And her shadow is 7.2 feet. 7.2 feet. That's her shadow. I drew inches there, excuse me. I'll draw that again. And that is not 7. Getting a little wild with my pencil. I always have trouble with it anyways. As if you've been with me for a while, you know that already. 7.2 feet. 7.2 feet. That's her shadow. Her height is 5.4. The house's shadow is 56, and its height is X. So just like we did before, I'm going to say the height of the house is to its shadow as the girl's height is to her shadow's length. See, if you think of it that way and you say it out loud, we're going to multiply both sides by 56. So we're going to get X is equal to 5.4 times 56, and that's divided by 7.2. And when you do the math on that, X is going to be equal to 43 feet. The height of that house will be 43 feet tall. Okay, objective 2. It's a continuation of our first statement of objective 2. A scale drawing is an enlarged or reduced drawing that is similar to an actual object or place. If you recall, this was in the definitions in the beginning. Floor plans, blueprints, maps are all examples of scale drawings. A ratio of a distance in the drawing to the corresponding actual distance is the scale. So the scale might be, and I think I said it before too, of the drawing. It would be like um, a mile per inch, or a foot per eighth of an inch, or a foot per quarter inch. But that's like a scale. So for every quarter inch you draw on the paper, that would be equal to a foot or something of that nature. Okay. Okay. Example 3: finding a distance on maps. The scale of the map at the right is 1 inch equals 10 miles. 1 inch is to 10 miles. Okay. Approximately how far is it from Valkarai to Wabasco or Wabasso? Valkarai to Wabasso. So you look at the map and you see Valkarai is way up here near the top, right up here, and Wabasso is down here. So what we're going to do is we're going to measure along the ruler because they're telling us it's 1 inch for 10 miles. So if you go from this point right here to this point right here where the 1 is, that's 1 inch, that's 10 miles on this map, okay, along the shoreline here. So let's go ahead and measure it. It says, so what do we want to do? We want to map, the map distance is 1.75 inches. So let's look at that. From here's Valkyrie. So this is the inch mark right here. This is 0 inches here. Here's 1 inch. And here's 2 inches. Well, we don't get the 2 inches. We get to 1 3/4 inches right there. So 1 3/4 inches is the distance, 1.75 from Valkarai to Wabasso. So the map distance is 1.75 inches. And we're going to let D equal the distance. How far is that? We know that it's 1.75 inches. Well, how many miles is that? Well, what do we know? We know that it's 10 miles per every inch. So let's draw this proportion out. Let's write it. So 1 inch is to 10 miles, as 1.75 inches is to D miles. We don't know how many miles. How many is it? Well, we're going to do cross multiplication. We're going to multiply the D through, and you're going to get 1D on the left. And we're going to multiply the 10 through, and we're going to get 1.75 times 10 on the right. That's our cross products. And when we're done, that's 17.6. D is equal to 17.6 or 17.5. Anyways, it's in that neighborhood. 17.5. That's the answer. So now we'll move on. Okay, so example 3, check your understanding. I'm going to have you just go ahead and stop the video again and try these. And when you come back, we'll work them together. But I'll read them before you leave. On the map above, it says, remember the map up here? I brought it down also. It's the same map on the right. Measure the distance from Grant to Gifford and find the actual distance. And part B to this is, if on another map showed the distance from Valkarai to Wabasso, but has a scale of 1 inch equals 5 miles, what would the map distance be between the two locations? They want the map distance. Now that you know the scale, they want to know how many inches is it going to be on the map. So think about that. Okay, when you come back, we'll work it together. Okay, so now that you're back, let's take a look at it. On the map above, or to the right, measure the distance from Grant to Gifford. Find the actual distance. Okay, so first we got to measure the distance. And so we look over here to the scale and we see, what do we have? We have yellow we're going to do. Let's use red. That'll show up nice. Grant is right here. I'm going to draw it down here, right here, right? And what is that? These are 1/8 inches, so this is a 1/16 of an inch right here, right? 1/4 inch from here to here's the 1/4 inch. There's an 1/8 of an inch. The little tick marks are 1/16 of an inch. 0.0625. Okay, so here's 1 inch, and we're going to Gifford. So from 1 inch, here's 1 inch to here. Plus we have from from this point, the 2-inch mark to Gifford, we have 3/8 of an inch. So this total is 1 3/8, 1 3/8 from here down. And then up to Grant, we have a quarter, a half, and we have a 16th less than 3/4. Okay, so we're going to have a quarter and a half. That's going to be what is that? That's 11 sixteenths. Okay, so I think it's going to be 1 3/8, which is in sixteenths is going to be 6 sixteenths. 1 6 sixteenths plus 11 sixteenths is equal to um, what do we have here? These are the sixteenths. We have the 1 inch, and 11 and 6 is 17. So that's one. So it's 2 inches and a 16th. Okay. So if you look up here, I have 2 inches and 1/16, 2.0625. Okay. So that's the measured distance. Now we say, what is our scale? 1 inch per 10 miles. 1 divided by 10 is equal to, so 1 inch is to 10 miles as 2.063 inches is to how many miles? We don't know. Some amount of miles, d miles, right? So in order to solve this, we've written the proportion and we're going to do cross product multiplication. So we're going to take again and multiply the d times the 1 over here on the left, and we're going to get 1d, and we're going to multiply 10 times the 2.063 on the right, and we're going to get is equal to 2.063 times 10. And then when we simplify, we're going to get d is equal to 20.6 miles. So Grant to Gifford is 20.6 miles. Now they ask an interesting question over here, and I'm going to erase this little bit of math that I was doing because it's not going to help us anymore. Okay. Okay, I think I have it now. And maybe I'll change to blue. So it says, if another map showed the distance from Valkyrie to West Wabasso, this is going back to the original equation. It's the 1.75 inches, right? Or 17 and a half miles. We see it right here. But the scale was 5 miles per inch. 1 inch is to 5 miles. What would the map distance be to the two locations? Now they want the map distance. We know what the distance is. We know that it's 17 and a half miles. But what they're asking us is, in the first problem, the distance was 1.75 inches. They want to know what are the inches going to be if it's a 5 mile scale. Well, you can, off the top of your head, you can say, well, that's probably going to be twice as far because each little increment, each inch is going to be a shorter distance. So we're going to have more of these shorter distances. And that would be correct. The answer would be right here. Instead of 1.75 inches, it would be 3.5 inches. But how would you do it mathematically? What would it really look like? So, and we're going to use dimensional analysis. Just the last section, if you missed it, go back and look at section 1 of this chapter. We go over dimensional analysis. So we're going to do and write this up using dimensional analysis. So I'm going to say, we know that the distance in each equation that we're trying to solve here is the same. It's 17 and a half miles. So that's where these two become equal to each other. They have that same distance. So what we're going to do is we're going to write 17 and a half miles is to 10 miles per inch. 10 miles per inch, right? We know that's what the original was. 10 right here, 10 miles per inch right there. So 17 and a half miles is to 10 miles per inch, as 17 and a half miles is to 5 miles per inch. Okay, that's the difference. And when you solve this, we're going to divide this thing. What do? We're going to multiply by the inverse to get rid of this denominator. And when you do that, you're going to get 17.5 miles right here times 1 inch per 10 miles. That's how you get the 1 inch. You flip this. When you divide by a fraction, you invert and multiply. You all remember that? So I've inverted and multiplied. So now I'm going to get 1 times 17.5. The miles are going to cancel, and it's going to divide by 10. So I'm going to get 17.5 times 1, which is 17.5, divided by 10, which is 1.75. That's the original equation that you were working with using dimensional analysis. So now for the second one, the new problem, 17.5 miles divided by 5 miles per inch is equal to 17.5 miles, same 17.5 miles, divided or times 1 over 5. And when you do that, you're going to get the 17.5 times 1 is 17.5, and divided by 5 is going to be 3.5 times. And it'll be 7.5 inches, right? Inches remain because what disappeared? The miles disappeared. The inches remained. So that's why you get 3.5 inches. 17.5 divided by 5 inches equals 3.5 inches. Okay?